So, today we will be discussing some problems on Gaussian curvature and the Codazzi and Gauss equations. So, I will start with a simple problem on Gauss curvature. So, you remember the Gauss curvature K is given by the formula B upon G. Now, what we have to show in this exercise, this is exercise number 1 in fact, that is 2 and this will be 3. What we have to show that is the following, that K equal to yes 1 upon G square into this scalar triple product of R11, R1, R2, scalar triple product of R22, R1, R2 minus scalar triple product of R12, R1, R2 whole square. This in fact follows directly from the formula K equal to B upon G. Solution is straightforward. We know that K equal to B upon G. So, I can write down K equal to 1 upon G into B11, B22 minus B12 square, and B11 is n dot R11, B22 is n dot R22, or you better write down R22 dot n. Here also R11 dot n, does not matter, and this one is R12 dot n square. And n can be written as R1 cross R2 upon modulus of R1 cross R2, which you can write down as under root G. Similarly, in this bracket you will write down R22 dot R1 cross R2 upon under root G. Okay. Then minus R12 dot R1 cross R2 upon under root G whole square. So, this product will be G. Similarly, here also you will be having G. When you take G common, you will be getting G square outside, and this is scalar triple product of R11, R1, R2, scalar triple product, R22, R1, R2 minus R12, R1, R2 square, and this is what you were to prove. So, just you need to remember that what Bij's are, and they are, and what is n, in fact it is R1 cross R2 upon mod G. So, you can straight away prove the relation. All right, now next is exercise number 2. Now, what we will be doing for exercise number 2, we have to recollect that Bij once again for exercise number 2. Bij, as I just showed you, is Rij dot n. And k equal to b upon g. So, once again you will write down this as you have to write down k equal to b11 b22 minus b12 square upon g, and we have just established that this comes out to be 1 upon g square into r11 r1 r2. I have just proved it, r22 r1 r2 minus r12 r1 r2 square. Now, if you look at this scalar triple product, these scalar triple product are in fact the determinants. Determinant of vectors r11, r12, r2. So, the first row of the determinant will contain the components of r11, the second will contain component of r1, and the second will contain the component of r2. So, it is a matrix. In fact, you have a matrix in which the components of r11 are there. So, this contains the components of r11. Similarly, the second row, this is the first row, this will contain the components of r1, this will contain the components of r2. What these components are, we are not writing them down. So, and this if I call it A, and this matrix, in fact, the matrix I call as B, the second one, the corresponding matrix. This is the matrix A, and here the matrix involved is C, and these quantities are the determinant of those matrices A, B and C. So, I will read it like this. This is equal to 1 upon g square into determinant of A into determinant of B minus determinant of C square, where I have just explained what A, B, C are. So, this can be rewritten as 1 upon g square into, now determinant of the product equal to product of the determinant. So, this becomes determinant of the product of the matrix A into B minus determinant of the matrix C whole square. Now, you have to look at the matrices A, B and C, so that you know what these rows will be. So, what will be the rows? So, here what will happen? You have to look at the matrix A, you have to multiply it with matrix B. This is matrix A, this is matrix B. When you will multiply the two matrices, the first row here will be multiplied with the first column, that will give you the first element, okay, and so on. Then you take the determinant, that will give you the same quantity. So, thus you have to write down the rows and columns of matrix A, B and C, and you will get the result immediately. So, it looks a little long in expression, but it is a very simple exercise. You can straight away do it. Okay. All right. Now, come to the third one. So, the computation I am leaving for the students. For exercise, yes, that is right, simple dot product. And now, for orthogonal coordinates, you have to show that Gaussian curvature will be this. So, to solve this problem, you have to look at the for Gauss equation. What we are given in this exercise, that the coordinates are orthogonal, that means G12 is 0. So, this equation, Gauss equation, will become simple when G12 becomes 0. So, when G12 is 0, this is the solution of exercise number 3. When G12 is 0, that is when coordinates are orthogonal. Coordinates are orthogonal. The Gauss equation takes the following form. So, the first term in the right side will be 0, and you will be having del minus, you can take common, minus half in fact, and delta 2 G11 upon del U2 square plus delta 2 G22 upon delta U11 square. Then you have these quantities minus GLM into these Christoffel symbols L11 M22 minus L12 into M12. What you have to do here, you have to resolve this Christoffel symbol under the condition when G12 is 0. You have seen in one of the exercises that the Christoffel symbols get a simpler expression under the condition G12 equal to 0. So, let me look at these Christoffel symbol. So, Christoffel symbol L11 will be what? In fact, you can, what you do is, you can vary L and M, both are dummy indices. So, if I look at this bracket alone, it will be what? It will be G11 into this bracket plus G12 into the bracket plus G22 into this bracket. But G12 and G21 both will be 0. So, this bracket will not contribute anything. You have to see only G11 into this bracket, G22 into this bracket. Okay. So, this can be rubbed off, and let us see what will be in this bracket. So, it will be 1 1 1 1 2 2 minus 1 1 2 square, okay, plus you take the second bracket, this is G22 into 211 into 222 minus 212 square. So, the only problem that is left for us is to compute these Christoffel symbol 1 1 2 1 2 2 and so on, under the condition that this G12 is 0. Let me look at this 1 1 1. So, this by definition is half of G1 M. M is a dummy index, but you cannot put 2 over here because G12 is 0. So, M is also 1. So, all indices are 1. So, delta G I k, so that will be 1 1 upon del U j means 1 plus same quantity minus delta G I j, that is all of them are 1 upon del U 1. So, what you get is that it is equal to half, and G upper 1 I have already told you when G 12 is 0 becomes simply 1 upon G 11. So, this is del G 11 upon del U 1. Okay. So, this you have computed. This is how much? This half G 11 into del G 11 upon del U 1. Okay, this is okay. Now next you can compute two. This one? No, oh, okay, this one, I am sorry. 1 2 2. So now you make I and j both 2 2. So this will become half G, once again it will be 1 1, 1 2 is not possible. I m means del G 2 1, so it is useless, plus del G j m means 2 1, that is also useless, minus del G 2 2 upon del U k means del U. So, only this one del U k means 1. So, this becomes 1 upon 2 G 11 into minus times into del G 2 2 upon del U 1. So, you have got hold of this also. So, this becomes 1 upon 2 G 11 into del G 2 2 upon del U 1. Okay. Similarly, you can compute this. What is this? G 112 whole square 112. So, once again half G 1 and 1 together here. So, I is 1, j is 2. So, I m means 1 1 upon del U j means del U 2 plus del G j m, j is 2 1. So, this is useless, minus del G, again I j is 1 2, this is also useless. So, Christoffel symbol here also is easy. So, this comes out to be 1 upon 2 G 11 delta G 11 upon del U 2. So, you have got this also 1 upon 2 G 11 into delta G 11 upon delta U 2. Similarly, you can compute those Christoffel symbols also. So, just you have to compute them and then you have to adjust these two terms with these derivatives. So, you can immediately get the answer. It is a matter of computation, nothing technical. So, I hope this can be done easily. So, the remaining computation I am leaving for the students. Okay. All right. Now, I can move on to the next topic, that is the in fact beginning of unit 4. This is curves on surfaces. As a fundamental theorem, I have to just state, I will not go into the proof. So, this is the fundamental theorem of space-time surfaces. Bonnet theorem involves some integration on surfaces. So, with that we have not done orientation of surfaces, we have not done. So, that is why we leave it. So, if you are given functions say gij's and bij's, how many functions? 3 gij's, 3 bij's, means if you are given 6 functions of 2 variables. So, if Gij's and Bij's are given real valued functions, are functions of u1 variable, let me call them u1 u2, and these Gij's satisfies this Gauss equation and Kodazi equation as well, which satisfy Gauss and Kodazi equations, Gauss and Kodazi equations. Then there exists a unique surface. Then for regularity we want G a non-zero, okay. Otherwise it is not essential, okay. And G means G11, G22 minus G12 square. You can write them down. G11, G22 minus G12 square is non-zero. Then there exists a unique surface, unique except in the position, except the position in space, except its position in space. There exists a unique surface whose first fundamental form is Gij into dui duj. You may call it ds square, and second fundamental form is Bij dui duj. In proving this theorem, there are several proofs of this theorem, but here also in proving this theorem we made use of the ordinary differential equations for uniqueness. So, now this was the last title of the third unit. Now we move on to the fourth unit after a break of 5 minutes.